All right, so thank you. So Penguin Philosophy, let art and science inspire. So I started this company because I believe in the inspirational power of art and science. I hope to one day live in a world where art and science become the key sources of inspiration in people's lives, which, when applied, will allow them to drop anti-scientific beliefs. The human race, as I'm sure we all know, is plagued with anti-science all around the world, like believing that the Earth is 6,000 years old, climate change denial, anti-vaxxers, all that fun stuff, virgin births. I know, we're still talking about this. It is my goal to promote science worldwide and to stand in opposition of negative sources of inspiration. One of my heroes and sources of inspiration is here tonight. Professor Krauss makes big ideas accessible, from early universe to general relativity, even though these subjects can sometimes leave us perplexed. He communicates in a way that's accessible. He also really knows how to piss off creationists. Please welcome to the Danforth Music Hall, Lawrence Krauss.
Thank you. Thank you. Hi, thanks. Okay. Thank you. Well, that's the show. Thank you very much. So what I thought we'd do, since I'm going to be with Matt later, is give a short talk on part of the new book, and because I don't have enough time to do the whole thing here, and I was just up north near the airport at a meeting where I did. So I thought I'd give you a taste of the greatest story ever told so far, and then we'll get to cover more of it in maybe that, and I don't know what Matt has in mind. And then one thing Travis didn't point out is that we want to give a lot of time for questions from you all, so that you can ask about anything you want. About the book, about science, about your sex life, or whatever the heck you were doing. But I wanted to start with this quote, which given the lights, I was going to say the hardest thing of all to see is what's on the screen. Anyway, this is one of my favorite quotes, which is which a filmmaker friend of mine, Werner Herzog, told me about. It's a naturalist book called The Peregrine, and it's about a peregrine. And this thing, the hardest thing of all to see, is what is really there, is really captures the perspective of modern physics, but this perspective of science in general, that the world we see is an illusion. And what science has been able to do in the last 400 years is uncover many aspects of that illusion. And it is truly remarkable that we've been able to do it, that we've been able to overcome our own biases and prejudices and do that, and that's what I want to talk about. Now, let's go, yeah, okay, I want to tell a story, so I thought I'd begin by copying, because I'll be doing that a lot, a good storyteller. So it's the best of times today, and by that I mean that the Large Hadron Collider is operating, as I'll talk about, and it hasn't created a black hole that's going to destroy the world, and that's a good thing. At the same time, it's the worst of times, and no, not Neil, and anyway, and we'll come back to this guy, or at least what I want to talk about is how science can overcome not just the illusion of reality at the forefront of physics, but the illusion of reality that unfortunately permeates our political process. And we have to use the same tools, and it's been so successful in one area that we need to use it in others. But this too shall pass, which is the other thing I want to emphasize to you. This too shall pass. And so, okay, so this is a window in the winter, which in Toronto you will recognize. When I gave a talk about this subject in Phoenix, they didn't know what it was, so I had to explain it to them. But so these are icicles on a windowsill, and what I want you to do to begin with is imagine what it would be like to live on one of these icicles, for your civilization to have formed on one of these ice crystals, say that one right there. And if your civilization formed and eventually had scientists and everything else, the physicists would explain that there's something very special about that direction. The forces on that crystal would be very different in that direction than perpendicular to that direction. And physicists would come up with models that explained how the forces changed. And theologians would explain why that direction was meant by God, And then there'd be wars fought in the name of God. Actually, people would argue whether it was that direction or that direction that was the most important one. But we can see with the benefit of the fact that we're not on the windowsill or in this ice crystal, that direction is just an accident. There's nothing significant about it. And the really amazing thing that science in the last 50 years has demonstrated is that's our universe. In not just in a sort of a vague way, but in almost an exact way. And I want to talk about that. And I want to pick up the story fairly late because I want to have time for our discussion. So I want to start with this guy here, which is fairly late in the story. Okay, you know him. Good. Richard Feynman, one of the greatest physicists of the second half of the 20th century. I wrote a book about him, and he's an amazing scientist. And he was faced with solving a problem which was this. As I talk about in the book at great length, science at that point had made great strides. We discovered amazing things, and one of the hallmarks of amazing things in science is when things that look different on the surface are shown to be the same. When things that seem very different are seen to be different aspects of the same thing, that means there's progress, at least in physics. And Maxwell and Faraday had shown that electricity and magnetism, which seem very different on the surface, are really exactly the same thing. And that led Einstein to show, or people following Einstein really, that space and time, which seem very different on the surface, are really the same thing. That means one person's space is another person's time. And all of these things are highly not intuitive because on our scale, electricity and magnetism look different. Space and time certainly seem different. I can go from London, where I just flew in, and back again, but I can't do a round trip in time as far as we know. But all of that had eventually been resolved, relativity and electromagnetism, and it was great. But then came along quantum mechanics, and quantum mechanics screwed everything up. Because quantum mechanics makes relativity seem sane. It really makes it seem simple. Because the quantum universe is absolutely crazy. At fundamental scales, the universe behaves in a way which is literally not understandable, and certainly seems absurd. But the basic principle behind quantum mechanics, which is important for what Feynman did, is that quantum mechanics is like, as I like to say, like Washington or corporate America, which are the same now. And that is that if you can't see it, anything goes, okay? And we're going to learn more about that with investigations, I hope, in the next few months in the United States. But that means that's all due to the Heisenberg uncertainty principle, which says if you measure a system for a little while, then there's certain things you can't tell about that system. No matter how good an apparatus you have, there's certain things you can't measure. If you measure a system for a short time, then you can't know exactly what its energy is. So what Feynman set out to do, and several others, and Feynman ultimately won the Nobel Prize for this, was to try and take this beautiful theory of electromagnetism that Maxwell and Faraday had developed and others, and make it consistent in the quantum world. Have a quantum theory of electromagnetism, and utilize the aspects of quantum mechanics. And Feynman did this, and he did it pictorially as well as mathematically. And this is the modern quantum understanding of why two electrons repel each other, something that had been understood classically 100 years earlier. So this electron, think of this as time, this electron repels that electron, so that it comes by and it repels that electron. But in the quantum world, this is how it does it. The electron emits a particle called a photon. A photon is the quantum of electromagnetic waves. Electromagnetic waves come in little particles called photons. Even though they're waves, they come in little particles, and they're called photons. So the electron emits a photon. Fine. The problem is an electron can't emit a photon. An electron sitting there can't emit a photon, because if it did, well, if the photon goes away and carries energy, where did the energy come from? Because the electron's still there. So there's no way an electron just sitting there can emit a photon. It violates energy conservation. But this is the quantum world. If you measure a system for just a little while, then you don't know the energy of that system exactly. And that means you can violate energy conservation, as long as it disappears in a time frame so short you can't measure that violation. So if you emit this photon, it violates energy conservation, but as long as that photon disappears in a time scale so short you can't measure it, it's okay. It's just like embezzlement. It's literally, right? You take the money out of the bank, you do whatever you want with it. as long as you get it back in the morning before anyone can see it, then you're fine. So the way to think of electromagnetism is the electron emits this photon, which we call a virtual photon, because you can't see it. If you could see it, you'd know there was energy violated. So it's there, but it's not there. Okay? You can't see it. It's a virtual photon. That virtual photon then gets absorbed by another electron before you can measure it, causing that other electron to be repelled. Great. That's the quantum theory of electromagnetism. But there's one other important aspect, and that is this photon has zero mass. Now that's important because electromagnetism is a long-range force. An electron here will repel an electron in Alpha Centauri, or at the other end of the universe. Electromagnetism works across the universe. And that's only possible in the quantum world because the photon is massless. Why? Well, because the photon is massless, E equals mc squared, and that means the photon can carry an arbitrarily small amount of energy. If it can carry an arbitrarily small amount of energy, then by the Heisenberg uncertainty principle, it can exist for a really long time before you would measure the violation of energy conservation. So it can travel from here all the way to Alpha Centauri and be absorbed by an electron there. So in the modern way of thinking, the reason electromagnetism is a long-range force is identical to the fact that the photon is massless. Now you know the whole theory. Okay, that's it. And it is the best theory in science. There's no theory that's better. With this theory, we can and that's the reason they won the Nobel Prize, but with this theory, we can calculate things from first principles and compare them with observations to 14 decimal places. And there's nowhere else in science you can do that. Nowhere. So this is as good as it gets. Okay? So everyone is thrilled. The world is understandable, and it's all going well, except nature, of course, throws in a little screw. And that is that the neutron is radioactive. Now, that should upset many of you. I remember it upset me when I first learned about it in high school, but it should upset you because you're made up of neutrons. Most of the particles in your body are neutrons. There are more neutrons than protons. The atomic nuclei of the atoms in your body are made of protons and neutrons, but many of the heavy atoms have more neutrons than they have protons. So they're the dominant particle in your body, but they're radioactive. If I took a neutron and held it out here, it would last 10 minutes. Okay? Boom. Now, some of you will notice painfully that you were listening to that music go over and over and over again for more than 10 minutes. And you were hoping that your neutrons would decay just so you wouldn't have to hear it again. But what gives? How come you're here? How come you're still here if your neutrons last 10 minutes? A remarkable accident of our existence. So let me draw a picture. So this is neutron decay. A neutron decays into three particles, a proton, and this is just a fancy way of writing an electron, and a neutrino. Now, the important thing is, and the remarkable accident is, that a neutron and a proton weigh almost exactly the same amount. A neutron is just a little bit heavier than a proton, 1 part in 1,000 heavier than a proton. And that means it turns out the neutron has its mass is just barely enough to be greater than the mass of the proton plus the electron plus the neutrino. If it wasn't, it couldn't decay into them. So it can barely do that. That's why this lasts 10 minutes. 10 minutes may sound short, but in the particle physics world, that's a really long time. And that's why we call this a weak decay. It's a weak interaction because it takes a long time to happen. But it's only weak in that sense because these masses are very close. So why are we here? Well, I now drop a neutron in a nucleus, and it gets bound. What does it mean to be bound? Some of you know. But what it really means is it takes energy to get unbound, right? If we're bound to the Earth here by gravity, if I jump down off the stage, it takes energy to get back up, and it takes more energy to get higher up. So you lose energy when you get bound. So the neutron, when it falls in a nucleus, loses energy. But E equals mc squared. So when it loses energy, it loses mass. And when it loses mass, because the mass difference is so close, when it's inside the nucleus, it no longer has enough mass to decay into a proton, an electron, and a neutrino. So it's just that accident of nature that the neutron and proton mass difference is so small that when you drop it in a nucleus, it can't decay, and that's why you're here. So carbon, nitrogen, oxygen, iron, all the materials that make you up, none of that would exist if neutrons decayed. But they're here and you're here just because of this remarkable accident. Okay, well that's great, but that means This is an important thing. And maybe this decay is interesting. It also is the same process that powers the sun. So it's also the other reason you're here. Because all of life on Earth is possible only because of the nuclear processes in the sun. So we want to understand this. But the big thing is that this means there had to be a new force in nature. Because electromagnetism can't cause this decay, and gravity can't. So there suddenly had to be a new force in nature. And if there's a new force, we need to understand it. And the first person to write down a theory to understand it is one of my favorite physicists from the 20th century also, Enrico Fermi. Enrico Fermi was a brilliant Italian physicist who was the last one who was equally adept at theory and experiment in particle physics and nuclear physics. Now, both of those fields have become so complicated, there's so much baggage that people do one or the other. I'm a theorist, but other people are experimentalists. He could do both. And he, in fact, was assigned during the Manhattan Project to create the first nuclear reactor, the first stable chain reaction, so that they could make an unstable chain reaction, a bomb. And so he built the reactor in the University of Chicago, actually, during the war. It was underneath a football field, which is brilliant, I always thought, because then if anything went wrong, you just kill football players. There's no loss. So it's good. But Fermi before that had written down the first theory of how this might work, and he submitted it to the journal Nature, and it got rejected, which is great because it gives people like me solace when we get rejected by Nature too. But Fermi didn't take it very well, and he said, "That's it. I'm not doing theory anymore." And he went on and did experiment, which was good for him because the next experiment he did won him the Nobel Prize in physics, so it worked for him. But nevertheless, his theory then was taken up by others, and they tried to make a theory of this new force. Now, the really important thing to know about physics, there's a few things I want to tell you, but one of them is that physics is like Hollywood. If it works, you copy it. And you keep copying it till it doesn't work, like Halloween 23. It's just, and so physics is the same. So if you got a good thing, let's copy it. So we have the best theory in nature. The very best theory we have, quantum electrodynamics, doesn't get better than this. So if you want to make the force look like this, you want to make it look like this. So let's make that decay look like this. So we draw a diagram, a Feynman diagram, trying to make it look the same. It's a little more complicated. The neutron decays into a proton. It's made of these particles called quarks, but it sort of looks like that. And then the electron neutrino come out of this at the end. And we can think of a particle being exchanged in that process, mediating that force, the same way as the photon mediates the electromagnetic force. But this force is very different than this force. This force is long range. This force is short range. It only works inside the nucleus. This one's, you can measure easily. We do it all the time. This one is very weak. Okay. Well, but if this one's short range and this one's long range, how can they look the same? Well, if I give this particle, this new hypothetical particle, a mass, then maybe I can explain it. Because if this particle is very, very massive, then let's think what that implies. When I emit it, it's very massive, and E equals mc squared. That means when I emit it, it carries a lot of energy. That means it massively violates energy conservation, and that means it can't live very long. It can only travel a very short distance before it has to disappear. So if I have a massive particle mediating this force, then the force becomes very short range. It's great. And I can explain the weak interaction working only over the nucleus and this working over the whole universe. Sounds great. The problem is this is a beautiful theory. This one is nonsense. It's nonsense because when you do the calculations for this, assuming this is a massive particle, here you get predictions that agree with experiment to 14 decimal places. Here you get infinities. Infinite answers, and physicists don't like infinite answers because we can't do anything with them. Mathematicians love them, but physicists hate them. And this was a problem that physicists confronted in the 1960s. And it's amazing to me that this was such a severe problem that the physicists actually were willing to give up this beautiful theory, this beautiful idea of quantum mechanics and relativity that had led to this on the atomic scale, and said maybe on the nuclear scale we have to throw out all of conventional ideas. Maybe none of it works. Because this is such a severe problem that they'd given up. And one of the things that makes this story great is, first, Donald Trump isn't in it, but secondly, one of the things that makes this story great is that it shows human foibles. Okay? A real other secret about science is that scientists are human. Don't tell anybody. And that means that scientists have biases and prejudices, and they're pig-headed, and they can go off in the wrong direction. But the science, the process of science, overcomes that personal bias of the scientists and drags them in the right direction. And in the story, when I was writing it, and maybe if you read it, those who read the book, I wanted to just shake these guys in the 1960s and say, don't give up the theory, because the right answer is right here. You have it. It's right here. But they couldn't see it because they were so fixated on things, and it took a while before the physics, the experiments eventually forced them in that direction. And the thing they couldn't see was physics from another area of science, superconductivity. In 1911, the Dutch physicist Kamerlingh Onnes discovered something remarkable. If you took mercury and cooled it down to 4 degrees above absolute zero, then something really amazing happened. The electrical resistance would drop to 0. It wouldn't just become small, it would drop to 0. Now that may not seem amazing, but it is. If I take a wire of mercury, when I cool it down I can make a wire out of it, and I attach a battery to it so I get a current flowing in that wire, and then I cool it to below 4 degrees, I take the battery away, the current continues to flow. And it doesn't flow for just an hour or a day or a year, it flows forever. It never ever stops. It'll flow for all eternity. And that just seems impossible. It seems magical. And Kamerlingh called it superconductivity. He had a flair for words. He could have been an ad writer. But it is really an amazing phenomenon. It took 50 years for physicists to understand it from the complicated interactions of electrons in these media of superconductors for that to understand that. Now, what's this got to do with anything? Well, now we can make superconductors that aren't just at 4 degrees, but actually are superconducting at dry ice temperatures. And then we can do neat experiments in high school physics classes. So here's one high school physics teachers like to do now, I think. We take a block of dry ice and we have a superconductor in it, a material that's superconducting at that temperature. And then you put a magnet on it and it floats. The magnet will float above the superconductor. Why is that? Well, it turns out magnetic fields cannot permeate the superconductor. They try and get into the superconductor and they die off very quickly at its surface. The same would be true for an electric charge, by the way. It would float as well, because electric fields can't permeate the surface of a superconductor. Great. It's a nice little experiment to do. And what that means, by the way, is the magnetic field lines get repelled and it floats. It causes the thing to levitate. What's this got to do with anything? Well, now I want you to ask yourself, what would it be like if you lived in that superconductor? What would the world look like to you? Well, if you lived in that superconductor, you develop physics, and you'd say, what's electromagnetism? And you'd say electromagnetism is a short-range force, because you put a magnetic field in that superconductor and it dies off. You put an electric field in that superconductor and it dies off. So you'd find electromagnetism is a short-range force. And then when you discovered quantum mechanics and tried to make a theory of electromagnetism, a quantum theory, you'd say, well, the particle that mediates that force is massive. And in fact, it's true. When you put photons, when you put light in a superconductor, light gets massive. The photon is massive inside of a superconductor, massless outside. Now this is the key that they didn't see, but now in hindsight it kind of becomes clear. We can imagine solving that problem that we had, and I like to liken it to swimming. So when you're swimming in a swimming pool, you zoom along, but let's say I filled the swimming pool with molasses. Well, you wouldn't want to swim. But if I forced you and you tried to swim, it'd be a lot harder to swim. You'd experience a lot more resistance because of the background. So now let's imagine that everywhere in the universe, there's an invisible field everywhere throughout all of space. And some particles, as they're traveling along, interact with that field and experience a resistance. And they may be massless to begin with, but when that field is there, they experience a resistance and it slows them down and they act like they have mass. So now, in that case, if that's true, we can draw a picture similar to the one I drew before, but I turned sideways now. Here's electromagnetism, the exchange of a photon, this is, between two particles. And here's that other interaction. Turns out there are 3 particles in the weak force. Doesn't really matter. But this is sort of decaying and producing electrons and neutrinos. And here's the particle that's conveyed. And now they look very similar, because now I can imagine, let's imagine that these W particles are not massive, that they're massless. But they interact with this background field everywhere in nature, and they behave as if they're massive. And then, when we try and look at the force that they convey, that force is short range. But now everything can be solved, because if these are massless at some fundamental level, then when we actually do the mathematical calculation of this force, it's identical to the mathematical calculation of what happens with that force. And instead of getting infinities, we get numbers that agree with the experiment. And we can calculate to arbitrary precision, 14 decimal places if we want. Everything works out. But not even better than that, if the mathematics looks the same, maybe they are the same. Maybe all these are basically represent exactly the same force. And maybe electromagnetism, which seems so different than the weak force, is not so different. At a fundamental scale, they're identical, something we now call the electroweak force. And two fundamental forces in nature that seem so different on our scales are really the same thing. And we live in a cosmic superconductor. That's remarkable. It would be the greatest unification of the 20th century. But at this point, it's still religious. Okay? Think about what I just said. There's an invisible field everywhere in nature. You can't see. Okay. See? And it would be religion, but it's not, it's physics. So in physics, if there's an invisible field, you can't just talk about it and pray to it. Okay? You got to find it. So if there's an invisible field, how can you find it? Very simple. Cosmic sadomasochism. You spank the vacuum. You spank it hard. Really hard. What do I mean by that? Well, in the quantum universe, for every field, there's associated with a particle. The electromagnetic field had the photons. So if there's this invisible field everywhere in space, if I dump enough energy into a single point, then maybe I can kick out real particles. And let me call that field the Higgs field. Okay? Then maybe I can kick out real particles called the Higgs particles. So how can I build something to dump enough energy into a single point? I build the most complicated machine humans have ever built, the Large Hadron Collider in Geneva. Now, if you go to Geneva, and you won't be able to see it in this, but there's Lake Geneva's over here, and the airport's over here. And if you get out of the airport, which I did recently in Geneva, you look out and you see beautiful farmland, but 100 meters under that farmland is a tunnel that's 26 kilometers around. And we take protons and we accelerate them around here to 99.999998% the speed of light, going in that direction. Then we take protons and we accelerate them to 99.999998% the speed of light in that direction. And then we try and collide them together at a few places in these rings. These protons are going around thousands of times every second. Here's the French-Swiss border. They cross that border thousands of times every second without passports or anything. And if Mr. Trump learns that, we'll be in trouble. So we built this thing, and we tried to do these collisions. And then there's a holiday that's an anachronistic holiday in the United States, July 4th. It means nothing cosmically. But it does now, because on July 4th, 2012, the Large Hadron Collider reported 50 events, discovery of 50 new particles that walked like Higgses and quacked like Higgses and looked like they were Higgses. And then in the intervening 5 years, every experiment that's been performed, these particles have exactly the property of the Higgs particle. So what we have discovered is that there really is an invisible field everywhere in nature that affects the properties that determines the universe that we live in, and that these two different forces really are the same. And this story, to me, is not only a great story, but the reason it's a great story is it represents what's best about humanity. This represents humanity at its best because we were willing to go into the unknown, to go in a direction we didn't want to go in, where nature dragged us, be willing to speculate and be wrong, and then be willing to build the most complicated machines humans have ever built just to test this idea. Just to test the idea, how do we get here? Not to make a better car or toaster. And this is important because often when I talk about science, this kind of science, people say, well, what good is it? doesn't make a better car. Doesn't you know, is it going to do something? And it's one of the sort of unfortunate things, at the same time it's fortunate, that science creates technology, because we wouldn't be here if it weren't for that, and most of us wouldn't be alive if it weren't for that technology. But but science isn't just technology. And the really important thing about science, to me, is the same thing that's so important about art and music and literature. It's nice to give this in a music hall. Because all those things at their best change our perspective of our place in the cosmos. Reading a good play, a book, a novel, listening to music, all forces us to think about ourselves differently. And that's exactly what science does. Science is a cultural activity, just like those things. And to me, that's the real importance of science, is that it represents what's best about being human, because those aspects, that's what makes humans worth being human, is discovering new things about the world and being surprised and enjoying it. And in this case, we didn't just discuss those things, but we were willing to build this most complicated machine. And in that sense, the Large Hadron Collider is just like the Gothic cathedrals of the 21st century. Gothic cathedrals are beautiful, and they were built over centuries by thousands of artisans from many different countries, all working together, in that case, for the glory of God. And they used the most complex technology at the time. It took a long, so many of these cathedrals fell down because people didn't know how to build these roofs right until they figured it out. Now, the Large Hadron Collider was built by 10,000 physicists from over 100 different countries, speaking dozens of different languages, many different religions, all working together just to answer this question, just to do this, spending their lives working together, and that those religions and cultures and languages don't get in the way, because science brings people together. Religion brings people apart, but science brings people together to do something like this, to find out about ourselves. And when you go there, this isn't the collider itself. This is just one detector. It's a large detector. There's a smaller detector called the compact muon solenoid. Here's some people here. It's not very compact. There's an equal amount of, in this detector alone, there's as much iron as there is in the Eiffel Tower. And you really feel like Gulliver when you're there, because everything is a big scale. You really can't sense unless you're there. But I do have a picture that's better because I'm in it. But it is just immense to visit. And if you get a chance to do that when the machine is down, you should. But the Large Hadron Collider is amazing in every sense. You can't have enough hyperbole. And there's a whole chapter in my book about it. For example, every second at the Large Hadron Collider, enough data is generated to fill more than 1,001 terabyte hard drives. That's more than the information in all the world's libraries. Every second, more information is being generated than in all the world's libraries, all the books that humans have ever written. And we have to amass and understand that data. And then if you take the tunnel itself, 26 kilometers around, superconducting magnets, but moreover, the tunnel has to be evacuated, so the vacuum in the tunnel is sparser than the vacuum outside the International Space Station. It's just amazing that we've been able to do this. And as amazing as that is, the best part about it is we're not done. The best part of the title is the greatest story ever told so far. Because unlike that other greatest story ever told, which I learned this weekend, it can also be called The Goat Herder's Guide to the Universe. Which I love that. That story hasn't changed. It's just as boring and wrong now as it was then. But this story changes every day. It'll be better tomorrow than it is today. Because there are young people, and there may be young people in this audience who tomorrow they'll discover things that change the story, and it gets better. And I kind of liken it to, I love art, and I love Impressionist art. It's my favorite kind of art. And I love it for a lot of reasons. But one of them is that far away it looks great, but you get close up and it really looks crappy. Okay? And that's science, okay? Because we now have developed this theory, this standard model of physics that explains every experiment we can see, that it unified these forces that on the surface seem so different. But every time we make new discoveries, we raise new questions. Sure, we now know that there's an invisible Higgs field. We live in this cosmic superconductor, unbeknownst to us. But why do we? Why did the Higgs field freeze in the early universe in a certain way so that the W particles get mass and the photons don't? Why did that happen? Why did it happen at the scale it did? We don't know. That's why we're continuing to run the Large Hadron Collider. And we'll do so for the next 20 years, looking for the possible answer to that. And if we do, it'll raise more questions. the story continues, and it gets better. And it gets better not because our minds come up with this. I mean, it is amazing that we were right about the Higgs field. I personally bet that we weren't. I actually had 3 papers in my desk that I wrote, waiting for them not to discover the Higgs field, because I was going to explain that. And nature, you know, decided it just seemed a little slimy to me to have this hidden field everywhere, but it is. And I was wrong, and that's fine. It's a good thing to be. We don't know where we'll go next, not because of the human imagination, but the imagination of nature, which is greater. But the key thing that science has done, and as I said, is change our perspective of our place in the universe. And really, the fact that there's a Higgs field has told us that we are really a cosmic accident in a way that, to turn back to my picture before, is identical. For these people, that direction was very, very special. For us, the world seems like it's designed for us. We are able to survive in this world because electromagnetism is long range, the weak interaction powers the sun. It all seems to be there for us, but at a fundamental scale, it's not like that at all. At a fundamental scale, the universe is inconsistent with our existence. It's only because this field froze in a certain direction in some mathematical space, and if it froze in a different direction, then electromagnetism wouldn't be long range and we wouldn't be here. Now, these people, these physicists here, might say, discover, ultimately, you know what, this direction isn't so special, it's an accident. And you can have icicles that point in any direction. And say they discovered that at 4 in the morning. And then at 6 in the morning, the sun rises, and it all melts. Well, that could be our universe. Because it turns out we've measured the Higgs field, and given what we can do, that field is tantalizingly close to melting. And if it does, then everything we see in the universe goes away. Every particle that has mass becomes massless. All the massive objects in the universe, from people to planets to stars to galaxies to aliens to everything, disappears. Like that. And that could happen. Now, don't get scared. Because, first of all, it's probably stable. We don't know for sure. But even if it isn't, if you do the math, it won't decay in a year or 100 years or a million years or a billion years or a billion years. Or a billion years. It's keep your diamonds, but it could happen, and the universe could return to that beautiful mathematical state, but not very exciting to live in. In fact, you couldn't, and that's okay too, because that's another misconception people have about the universe and nature, is that somehow it's evolved in some way, and we're the pinnacle of the universe, and it's going to be this way forever. It's not. This too shall pass. And everything we see could disappear. And the future, for us, could be completely miserable. But isn't it amazing that we have discovered it before it's melted? Now, this idea that this universe we see, which seems so beautifully designed for us, is not designed for us, is not new. Okay? It goes back in science in a lot of ways, especially to biology. This issue of design is something I want to spend a few minutes on, because it'll segue nicely, I think, into the discussion that Matt and I will have next. We look for design, we humans. We see beautiful things and they're designed. These Christmas ornaments are designed. Clearly, intelligence. But of course, they're not Christmas ornaments, they're snowflakes. You just take polar molecules and you freeze them and crystals form and you form these beautiful patterns. No design. But you say, okay, well that's different, but I can tell human things are designed. I can take architecture. Take Buckminster Fuller Dome. Okay, I remember when I was growing up, everyone had a Buckminster Fuller Dome in their backyard, the hippies anyway. And they did neat things in the Buckminster Fuller Dome. And all that. And that's right, it's great. But now take soot. In soot, there's a molecule, carbon-60, Buckminster fullerene. It's naturally occurring. And nothing could be less designed than soot. Okay? And so we have to be very careful when we look for design. And this has been a problem for science for a long time. And of course it is for cosmology now. But the person who first demonstrated that problem could be resolved without design was, in my opinion, one of the greatest scientists who ever lived, Charles Darwin. I put him above Einstein, even though I'm a physicist. Charles Darwin discovered that, in fact, the apparent design of life, that life appeared to be designed so beautifully for the Earth, was an accident. And in what I think is one of the most beautiful paragraphs in any book about science ever written is the last paragraph of The Origin of Species. It says, "There is grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one, and that, whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. It's a beautiful statement. It was true for biology. Natural selection produces this incredible diversity of life on Earth that seems so designed. But it's true for physics. The incredible diversity of structures we see, from people to galaxies that have all evolved from a simple beginning. So simple, in fact, they couldn't have been there at the beginning. In this case, if there hadn't have been this accident of nature of this field freezing in a certain direction. And that's, so this idea that the apparent design of the universe is an illusion is really important, and science has uncovered it. And it really has discovered that the universe that we see is an illusion. But scientists are also myopic, and it's worthwhile realizing science is a product of its times as well. And in 1863, in a letter to Joseph Hooker, Darwin said, "It's mere rubbish thinking at present of the origin of life. One might as well think of the origin of matter." I get paid to think of the origin of matter. It was rubbish to think about it in 1863, but it's not now. That's because the story's gotten better. And there are questions that seem like rubbish now. I get told all the time, science is never going to explain love or whatever you want it to explain. And how do we know? We don't know until we try. And what may seem absolutely unfathomable today, 100 years from now, will seem obvious. Only if we continue to do it, though. And that's my concern that I want to sort of end with, because I'm particularly concerned about the present time. Obviously in the United States, but other countries. But this cultural pursuit, of which science is a part, is essential, but it's unvalued by governments. And for example, in the United States, in the current budget that's just been proposed, the science that all this is about, particle physics, is part of a field that's going to be cut by 20%. But that's the department that funds that is called the Department of Energy, which funds energy research. But it also is the chief funding source for all physical science in the country. All the science that's going to produce the economics 50 years from now is being cut. But it's worse. The National Endowment for the Arts being cut to zero. The National Endowment for the Humanities cut to zero. Corporation for Public Broadcasting cut to zero. Institute of Libraries and Museums cut to zero. All of that. You add that up, that's $1.82 billion that's being saved in this purported budget. At the same time, there's a line item, $2 billion, the first installment on a wall with Mexico. So to save us from these imaginary hordes at one border, we're willing to give up all the things that really matter, the things that really make America great. The things that will make America great are not the walls we create, but the ideas that change the way we think about ourselves, the cultural ideas we present. And the best discussion, the best comeback to that I've ever known was from this guy, Robert Wilson, who was director of the first big accelerator in the United States, the Fermi National Accelerator Laboratory, the largest one in the world before the one in Geneva. And in the 1960s, he was asked by Congress, will it aid in the defense of the nation? And here is what he said. No, sir, I don't believe so. It has only to do with the respect with which we regard one another, the dignity of men, our love of culture. It has to do with, are we good painters, good sculptors, great poets? I mean, all the things we really venerate in our country and are patriotic about. It has nothing to do directly with defending our country, except to make it worth defending. And that's the point. These are the things that make us human. These are the things that make life living. And if we give them up, the future, the greatest story ever told, will end. The future is not going to be better than the present. And so I'll end with two quotes. The one I begin my book with, which is a quote from Virgil, the beginning of the Aeneid, which I learned in Latin because I grew up in Canada and I was educated. That's an easy applause line here. These are the tears of things, and the stuff of our mortality cuts us to the heart. But the next line, which I had not remembered, what a friend of mine reminded me of later, which I end the book with, is more interesting. Release your fear. And that's what we have to do. We have to fight the fear that's being generated by politicians and others, the fear that science will destroy faith, the fear of the unknown, the fear of aliens, not up there, but around us, we have to realize that the universe is terrifying and wonderful, and we should go into it with our eyes open, wherever it takes us, because that's the human journey that's worth continuing. And wherever it takes us, even if the future is miserable, we should enjoy that journey, and we should enjoy our moment in the sun. Thank you very much. Thank you.
How you doing?
Good. It's nice to have you up here, Matt.
I'm thrilled to be up here. Thrilled.
I'm always amazed.
Amazing.
I have to say, I'm just always amazed when the intermission's over and someone's still here, so it's really nice.
So this is actually the second time I've seen this portion of the talk.
Yeah.
And I like the fact, I understand a little bit more about it now than I did yesterday.
Good.
And I understood a little bit more yesterday than I did before that. But one of the things is that it always reminds me, as I learn more and understand more, I also learn that there's a whole lot more that I don't know. And if this keeps up until I die, I will eventually realize that I pretty much know nothing, even though I know something, and that's really frustrating. Because I've improved, my understanding's improved, and yet somehow it got worse.
But that's great. That's called learning.
That's what I was thinking.
Yeah, the less, the more that's the difference between you and Donald Trump. Okay.
That's the difference?
Well,
the one difference?
There's one. I was trying to think of them. No, but that's at least one, because he doesn't know that he doesn't know, and that's the scariest thing.
It is. I called him the Dunning-Kruger president on Twitter.
Okay, yeah.
It is very much that. For those of you who don't know, look it up. You'll love it. I thought I wanted to start with talking about the first time we ever met, because in hindsight, for me, it was probably a little more obnoxious for him than it was for me. It was Imagine No Religion 2 conference in Kamloops, British Columbia, and our flights were supposed to arrive at about the same time, and so they had a limo there waiting. And then my flight just kept getting delayed and delayed and delayed, and they made him sit in the airport waiting for this guy who he doesn't know, who he's supposed to share a limo with, and he doesn't, And someday you'll have to tell me exactly what was going through your mind, but I finally show up, we get in the car, and so now you have one of the world's eminent scientists and a guy who's probably better versed in philosophy than certainly physics. And what did I do? I'd like to ask you some questions about this idea about a universe from nothing.
Yeah.
Which I'm sure he'd never heard before by some jackass that doesn't know what he's talking about. And luckily it didn't make him hate me, and so here we are.
Yeah, no, but waiting for you made me hate you.
Oh no, when I finally did show up and we got in the car, I was sure that he was going to hate me for the rest of our lives, for the
I think I'd flown from Australia, so I was a little tired, and yeah, but I used to do that a lot.
So I thought we'd actually start with that. Tell us about a universe of nothing in 20 seconds.
Great.
Fix us all.
Well, I'll tell you, I'll tell you one thing that is interesting, at least, maybe one thing, that when I wrote A Universe from Nothing, there were speculations I made about the universe that, based on what we thought we knew, that are now much more firmly grounded, which is really neat. And the discovery of the Higgs field, which occurred after that book was written, is an example, because the fact that empty space can have this field everywhere in it, it demonstrates that empty space is much more interesting than you'd imagine otherwise. And in fact, that kind of field is intimately related to the kind of field that explains the very beginning of the universe. So the supposition that there could be any kind of field in empty space was something we thought might be the case, but we didn't know at that time. So it's nice to know that the book is even more right than it was. I mean, it's less speculative, let's put it that way. And the other thing that's probably, because I'm not going to go, I'm going to be a politician, I'm going to avoid the answer to your specific question, because I'm not going to talk about a universe from nothing a lot, because that would take a lecture, except to say that the universe can come from nothing without any supernatural shenanigans, and that's amazing, and we should love that fact that science has shown us that you don't need God to make a universe, and that's amazing. But one of the other things that was in the book, which is some things that I've done with debates with some people that I know you like to debate or would like to debate.
I honestly don't care if I debate him at this point.
Yeah, okay.
He's beneath me.
Yeah, he is beneath you, well beneath you. That they say, a number of theologians often say that we created the multiverse because, we don't like God, but it's just an excuse for God. And I always say the difference is the multiverse is well motivated. But God isn't. But and the multiverse might explain something, and God doesn't. But it still sounded metaphysical. But what's really kind of neat is in the interim, because of another great discovery, which I've talked about in other lectures at various times, the discovery of gravitational waves that we've just made, gives us a hope of discovering gravitational waves from the Big Bang itself, which would allow us to look back in time, back to a millionth of a billionth of a billionth of a billionth of a second after the Big Bang. Really see the very beginning of the universe. And test our ideas and basically be able to indirectly test to see if there are other universes. At the same level as we indirectly knew atoms existed well before we could ever see them. We can basically test all the ideas that make 55 predictions and test them, and the 56th prediction is, if all these things are true, there must be other universes. And so it's really, for me, it's amazing, because we'll take this really metaphysical idea and make it physics. And that's all happened in the last 5 years. The story gets better.
And I'm going to push back a little bit.
Good.
From the standpoint of lay people. You're welcome. There's this perception from people who don't understand this stuff that what a number of physicists are doing is magic or BS. For example, when you talk about the photon and it being massless, that it's roughly the same as embezzlement.
Yeah.
And when you talk about a universe from nothing and you talk about quantum fluctuations, as soon as you put something there, it's not the same nothing that like philosophers would talk about, even though in some sense it may well be.
Yeah, I mean, as you know, philosophers got mad at me and still are.
Oh, yes.
Because I made a joke about them in that book where I said that, I talked about this, and I said philosophers and theologians would get mad because they're experts at nothing.
But that's... And see, now I have to push back on that too, because when it comes to philosophy and science, I go both ways. Mm-hmm.
Yeah.
Hey.
I'm not touching.
There's this... Well, I don't want to skip ahead to the question I wanted to do after this, but on this idea, when there's something so incredibly foreign to the people who haven't bothered studying it, that it almost sounds indistinguishable from the magical metaphysical stuff that others are talking about.
I think Arthur C. Clarke said that once, that a sufficiently advanced civilization everything they do would seem like magic.
Be careful, because now you're putting yourself in an impressively advanced civilization and me not in that civilization.
And one of the things that I didn't talk about here, although you've heard me talk about it and it's in the book, is this notion from Plato that I begin the book with, that Plato imagined us being in a cave that looked at this wall, could only see the shadows of reality. And I'm not going to go into the whole thing here, but he did say that if you were dragged out and saw the light and saw the real world and tried to come back and explain it, people would think you're crazy. And it is a fundamental problem that the realm of the universe that I deal with in my research, at least on a daily basis, is so far removed from human experience as to seem unintelligible and also impenetrable. And I think that's one of the reasons that's one of the reasons I write books, but that's one of the reasons I told this story. And it's a longer story than my publishers wanted me to tell, because I think if you can show how we did it in baby steps, to get, start with the things we can measure, electricity and magnetism, and show by a series of steps how we get so far, then it seems less like magic, because it was really human activity with a lot of little baby steps, which is what the other thing that science is normally not portrayed to be. It's all these scientific revolutions, but it's not. It's little baby steps done by individuals, often wrong, and you can get imperceptibly from here to there. It's like you and I were just with Richard this week, Richard Dawkins this weekend, and it's like, as he often says about evolution, there's speciation, species change, but every animal is the same species as its parent. But by imperceptible changes, you go from one species to another. But at every instant, you don't see the change. But eventually, you make such a change that one species is unrecognizable to the other. At least they don't want to have sex with it anymore.
So, let me see if I can actually stick a bow on. Sorry? Are we being heckled already?
Someone's objecting to interspecies sex, I think is right.
Oh. Okay. I'm fine with it if you can actually find a way to get consent, as we found out on last week's show. So let me see if I can put a bow on this, because while I frequently said I don't claim to have any expertise in anything, and if I'm good at anything, it's taking complex ideas and distilling them down so everybody can understand, because that's what I have to do for me to understand it. There are things that you say that I do not believe, not because I am convinced you're wrong, but because I don't understand them sufficiently to say that I believe them.
Well, here's your first problem. You should never use the word believe.
No,
so, never use the word believe.
Oh, no, now we're going to
No. At least a scientist should never use the word believe, because things are either likely or unlikely. And that's it. We don't believe anything. I certainly don't believe anything.
Are you convinced that something's likely?
No, I have to be convinced that something's likely by the evidence.
By belief, belief is the state of being convinced that something is likely
Well,
true.
if you want to call that, but I think, and I think you're right in a general sense, but I have a problem with using words that have a lot of emotional baggage associated with them.
Me too.
Yeah, okay.
But I'm okay with belief because I think we can make a good case for using it, that there's a distinction between I am convinced this is the case, which is a fine way to say it. You don't have to say belief. But if you're consistent about using the word belief,
I'll buy that. I just think it's fine.
I've won another debate. I'm done.
Yeah, that's right. No, actually, I was going to point out it's okay as long as scientists don't use the word.
Yeah.
I mean,
I don't want to see
heathens like you could no. I mean, but
philosophy heathens like me.
Yeah, philosophy heathens. No, but I think it's important. And scientists can use the word in a popular context, but never in the context of science. And it's taken me a long time. I still sometimes do it, but it's really important that we point out the belief, at least in science, that religious sense of belief, the faith in things unseen and unmeasured, is not really there. Now, even that, of course, is not 100% true, because if you're a theoretical physicist or an experimental physicist working 25 years on an idea, you have some faith that it might be true, or you wouldn't be able to spend. But hold on, but there's a fundamental difference in that sense, that the faith is eminently shakeable. That's the great thing about science, is because the minute you have that idea and you've worked on it for 20 years and you find out it's not true, you just throw it out like yesterday's newspaper. You don't hang on to it and cut heads off or anything like that.
So, faith is a word that I actually don't use.
Excellent. Well, I don't either, but I wanted to point out that in some sense you need to have some, you can call it intuition.
I can go, okay. Yeah. So faith is the excuse people give for believing something when they don't have a good reason. If you have a good reason, you just give the good reason.
Well, yeah, but the problem...
So what
we rationalize our reasons. So reason is a slave of passion. And so we all rationalize things we do, and we say, boy, we have a good reason for doing that, and then afterwards we realize we're wrong.
Oh, yeah, I absolutely agree.
And so, but what I mean is, even in science we do that. I don't want to pretend that science isn't a human activity. That's why I said it. So some of those scientists were driven by the passion, but in the wrong direction.
So what theists try to do is pretend that we all have faith. Scientists have faith and they have faith. Because what they're saying is we are convinced of things in the absence of absolute certainty, and that's what they want faith to be.
Yeah.
The problem is the things they are convinced of in the absence of absolute certainty, they have no good reason for. And the things that scientists are convinced of in the absence of absolute certainty, they have very good reasons to. And so instead I say I don't have faith in anything. I have reasonable confidence in things based on previous experience and evidence. So in the same way that
likely
you want to
or
avoid...
unlikely?
Yes. I don't use the faith word.
Yes.
I fight against it. I'm okay with the belief word as long as we define it specifically as I'm convinced of something.
Okay, so that's a great semantic discussion.
I'll call it a tie. But that leads to another question. I'm constantly asked from skeptics and people who are concerned about how to do critical thinking and skepticism, I can't possibly have the time to become an expert in everything. Which experts do I trust? Which journals do I trust? All these other things. And for me, a lot of it comes down to the fundamentals of education. How do you think we can best go about, the people in this room and outside of it, begin to fix the fear of scientific education, the lack of respect for it, getting people to recognize that the fact that scientific findings change as we learn more is a good thing and not a bad thing? How do we start working towards fixing that?
Yeah, I mean, there's a lot we need to do. And what first we can do, the way we fix it, is by not teaching science badly. And I mean by that I think science certainly is taught incorrectly, at least it was when I was going to school, and I think still too much. In the same sense that I think all of our schools are outdated in the way we teach things. We teach things as if the information that a teacher is telling you matters, and it doesn't. you get the information, more information from this. What you need is the process, but you get more misinformation, and you need the process to distinguish between the two. And what you do is you take, the reason people are afraid of science is because, first of all, it's taught like, Einstein saith, and it's just like the Bible. But instead, we need to teach it as a process of discovery. Instead of teaching facts, we ask questions. And everyone loves the process of discovery, so teachers say, how does this work? Let's figure it out. It becomes a puzzle-solving process. It becomes something that everyone naturally enjoys. And we see that the scientific enterprise is not a set of facts, but it's a process for deriving facts. And it's that process that matters, not the facts. And then once you learn that process, there aren't alternative facts anymore, because the process is there. And I think that's really an essential part. And you need to have people be comfortable enough to teach that process. And part of that means being able to say, I don't know. Which I know we've talked about.
There's this fear of I don't know. How many people were in school and you were terrified of being called to the blackboard or give an answer because you don't know? And one of the things I think we need to change is getting rid of that fear in children of the I don't know answer, because quite often it's the correct one, and we should applaud that and encourage this spirit of discovery and acknowledgement that I don't have an answer.
And you know who's more afraid than children of the I don't know? Teachers and parents. Because how many parents, when your kid asks you a question, and you'll want to give them an answer. I like that Calvin and Hobbes thing where his father always gives him crazy answers. But it'd be fun to do sometime. But to someone else's kids. But it's I think a teacher, when a student asks them a question, doesn't want to say, I don't know. But that's the best thing a teacher can say, and then follow it up with, hey, let's figure out maybe how we can find the answer together. And it'd be a process of joint discovery. And parents, again, I don't know. Be comfortable with saying I don't know, because you don't. And and not knowing is one of the most exciting things about being human, because it means there's something left to learn. And I have often said that as a theoretical physicist, the two most exciting states to be in are either wrong or confused. Because that means there's something interesting going on.
So this is especially intriguing for me, because we've interacted a few times. We probably haven't spent as much time together as we have in the last day or so.
Yeah, it's true.
And I know that he doesn't have time to watch all or probably any of my stuff. And
when I'm on, no, I was going to say when I'm on it, but I see where we're going.
The same is true in reverse. But I don't have kids, but people will call into the atheist experience and say, oh, what should I do about kids and my friends' kids and everything else? And what I encourage them to do is, when your kids ask you something you don't know, say, I don't know, but let's go find out.
Yeah, same thing.
Encourage that spirit of discovery. To kind of leverage something in your talk, when I said before that, I don't believe you, or I'm not convinced because I don't have the sufficient understanding, I liken that to the fact that Maxwell's work was required to give Einstein the tools, to give Feynman the tools, to get, if somebody had tried to go back to Maxwell with this idea, the things that you're talking about, it would have been indistinguishable from religion almost.
From religion, probably, or certainly from magic.
Yeah, magic would be better.
Which I know you do, and I've seen you do very well. But he's a good magician. I'll tell you, we just did some card tricks for me beforehand. I'm sure we could just forget this, and you could come out and do some magic. But
if somebody wants to see something,
but it works both ways. I think it's really important to realize how there's that building process that no knowledge has ever come from revelation. Not one iota of knowledge about in human history has ever come from revelation. Einstein didn't have revelations. Einstein, required the results of Faraday and Maxwell, and then other experiments. And it always happens. There's no one. If you locked physicists in a room for 50 years and asked them to come up with a theory of the universe, what they come up with would be first of all far more boring than the real universe, but most certainly wrong. And it's because revelation doesn't reveal anything. Now, you can reflection reveals things. You can take knowledge, reflect upon it, and maybe get wisdom, or something like it, or get insights about yourself. But just thinking, pure thought, just sitting there and going does not yield revelation. And sorry, Sam Harris, another Buddhist, but anyway.
Well, here's another area where we've echoed each other, and some of you have heard me say this, and I heard you say something very similar yesterday, and that's this idea that people who claim that they've got a revelation from God or let's say they didn't even get a direct revelation from God, but they think that their holy book revealed something. It provides no substance until it's verified, which means even if there was a God who was revealing things to you, you would have no way of knowing. It doesn't become knowledge, it doesn't become accurate until you actually put it to the test. So, and this is where I'm in agreement with what Jerry Coyne said yesterday, which is science may in fact be the only way of knowing.
Oh, I get rid of the may.
I am slightly more nuanced in hedging my, but I think it is accurate that it is.
Well, and by science, and it's really important to point out what science, and Jerry and I have the same definition of science, which is, for me, science is just empirical investigation combined with reason. That's science. Investigating things based on testing, empirical evidence, retesting, and using logical analysis to analyze those results. That's science. So for me, science is very broad. And for some people, that might encompass other areas. But that's the process by which we learn things about the universe, which I call knowing. And even this learning about yourself is still doing that same thing, right? You're still asking questions and testing when you try and learn about yourself. You're not just closing your eyes. You're asking, well, why did I do that yesterday? Do I really crave that kind of attention all the time? And anyway, yeah.
Why did I rush up to them? We were joking earlier because yesterday at the Imagine No Religion 7 conference, we decided we didn't want to do anything repeat, and I was up directly before him, so I did a magic show instead. And there were a number of issues and comments, and now I've completely forgotten where I was going with that story.
It was good, though. I was enjoying it up to that point.
If you want like a 50-cent refund for that mistake, talk to Lawrence. So I've heard you say before, or I think I've heard you say before, in response to questions that are posed, particularly some that fall into the realm of philosophy, that you find some of them uninteresting.
Well, look, I always get it. Look, philosophy is useful. Philosophy is not. Philosophy is useful. Philosophy is reflection. Critical is questioning, reflecting, and it's reflecting on knowledge usually, and then coming up with good questions. So philosophy is useful in those areas of human activity where the questions aren't yet well defined, because philosophy provides us a good tool to come up with good questions. And therefore, my friend Dan Dennett is a philosopher who deals with the brain, and the brain consciousness is an area where really we don't understand anything very much. The proof why you can tell how much we understand in a scientific field by how many books are written about it. If there are a lot of books, that means we don't understand much. And because you only need one book on quantum mechanics, and that's it. But anyway, so in brain science, there's a lot of questions, and you can actually drive forward research in neuroscience and psychology and with philosophical questions, and that was true when natural philosophy was natural philosophy and physics. But physics is gotten to the point where the real questions aren't asked by philosophers because it's so much down the road that the real questions require an intimate knowledge of the physics to be able to ask the kind of right questions. And philosophers of physics, of which there are some, and I know I'll get in trouble because I do when I say this, they ask them interesting questions themselves, but it has no impact on the physics. Zero. Because most physicists can't spell philosophy. Okay? And I have to say, in certain areas of the philosophy of science, it has very little impact on the other philosophers. It's a field where they talk to each other. Now, they do they're very interesting sets of reasoning and thinking, but I can tell you as a fact that there's nothing that's come out of the philosophy of science in the last, certainly since I've been a physicist, that's impacted on physicists. And that's not a judgment. That's not a value judgment. It's just a fact. The physicists don't read the philosophical literature. And
well, if you don't read it, how do you know nothing's come out? No, I'm just...
No. I mean, I'm saying is it's by coming out of it. I mean influencing. By what I mean by that is influencing the work that's being done. And even my learning, what I know about philosophy of science. Of course, I read Kuhn and other people, but I learned much more about the philosophy of science by my mentors who were scientists, from Feynman and other people. I learned much more about the way science is done, how questioning is done, and the kind of questions that might be fruitful. I've learned by the scientists who've taught me, and not by philosophers.
And if we start to merge those two, you get to things like Karl Popper and the ideas of falsification. But that doesn't exist without Hume, in the same way that Einstein doesn't exist without Maxwell.
Yeah, no, look, I don't want, and that's the point. There's a rich human intellectual history, and it's all part of the wonderful tapestry of being human, and that's what I was saying earlier. So I don't think that philosophy is uninteresting to read. I read the Bible too. I mean, it's all part of. No, and I don't want to put them in the same sense that way. But I mean,
Thank you.
But you know, it's true that science has grown out of philosophy, but science has also grown out of religion. And so some people just meet and say, well, how dare you talk the way you were, because the early scientists were all religious, Newton was religious, and the first thing is that, well, that's because the church was the National Science Foundation of the 16th century. I mean, there was no universities except church-supported universities, so it's not too surprising there was that religious connection. But more importantly, big deal.
Yeah.
I mean, children grow up. So science grew out of religion and to some extent philosophy, but it's grown up. And happily, children cast aside the things their parents taught them or made them think about, and they become adults. And so it's absolutely true that science owes religion, in some sense, a debt, historical debt, but it's an ancient one, and we just throw, just bury it now.
This isn't the path that I intended this to go
Good.
down, but I love it.
Yeah, good. That's when it's best.
I remember a call to the show one time where I had said something, and somebody asked, well, Isaac Newton believed in God. Do you think you're smarter than Isaac Newton? And I said, yes.
Yeah.
On the subject of God and perhaps alchemy, I now know more about those subjects
know a lot
than
more
he
than,
did.
we know a lot more than Newton, absolutely.
I am smarter because of Newton. That
Yeah.
doesn't mean I'm more brilliant or more insightful or I'm likely to change the world in the way he did, but colloquially speaking, yeah, I'm smarter than Newton on God. What kind of statement would it be about the world if we hadn't gotten any smarter in the intervening years?
And Newton, by the way, and I talk about Newton in the new book, but Newton was crazy. He would be hospitalized now. There's no doubt about it. No, he was really a crazy man. But he also was basically full-time, not just alchemist. He spent much more time on the Bible than he did on physics. I mean, he was convinced that there were secret messages in the Bible that only he understood. He was really a full-time theologian and a part-time physicist, and I've often said if he spent more time as a physicist, he might have made a name for himself.
Now, I'm somebody who actually I'm a huge fan of Dan Dennett. Hopefully I'll be on stage with him one day, because we've communicated by email specifically about the free will issue, which I'm not going to go into.
Yeah,
there was a big...
You're free not to.
I was the lone compatibilist at INR 5 standing up having an argument against Krista Carlo and Jerry Coyne and Richard Dawkins. I'm like, how does that happen? How weird is my life that I end up defending that? But I do find some of the questions interesting, and I know Dennett's talked about intuition pumps, and everybody loves various thought experiments. I was talking to actually my friend Lee the other day about the problem of the ship of Theseus and how it relates to identity, how many parts in the ship can you change before it's different. The Star Trek transporters, which my wife, when we go to happy hour, if the concept of identity comes up, she knows there's going to be a discussion about whether or not you step in a transporter, are you committing suicide? This is why she doesn't go to happy hour with me anymore. It's a conversation, I kid you not, that came up week after. It's like only thing that geeky atheists want to talk about, and so I can understand why people are like.
Where did you first start thinking about that?
What's that?
When did you first thinking about the Star Trek transporter? No, it's all right.
My friend gave me this book called The Physics of Star Trek.
That's all right.
And I knew nothing about the author. I would have never imagined reading the book that he'd be sitting up here with me today. But throughout some philosophical discussions, I find it interesting because primarily when I view philosophy, I'm more focused on the thought experiments, the things that makes people think. I love to make people think. I love to confound expectations. It's one of the reasons why I love doing magic. It's one of the reasons I do things like this. I mean, we agree on a lot. We're not going to agree on everything. If I talked to people who I agreed with on everything, I would never learn anything. I wouldn't even be able to learn that they're wrong or how I can understand that they're wrong without engaging. Now, I'm not by any stretch saying that you should spend your time engaging with people who you think are wrong over and over and over again, because I like my show and I don't want you to take it over. you get to decide what conversations you want to have and how you have them. And the advice that I gave yesterday, briefly, was listen charitably as possible. That doesn't mean you should be a doormat for people to walk over. Try not to pretend like you can read minds, like you can tell what their motivation is. Oh, you're only saying this because, in the same way that if somebody tells you, oh, you're an atheist because you were mad at God. No, I'm not. I wasn't any more mad at God than I was at Voldemort. Yeah? So don't pretend like you can read motivations. Ask lots of questions. And the one thing is, you don't owe anybody an explanation or an argument. And so if people are pushing at you and you're no longer comfortable with it, you get to stop it. And you also get to say something that I love to say, which is, that's an interesting point. Let me think about it and get back to you. And then think about it and get back to them because you need to do what you're saying you're going to do. For me, philosophy is primarily about my fundamental love of philosophy comes from issues surrounding epistemology. How do we know what we know? What are the foundations of logical reasoning, and what can we learn from those? The most recent video I put up, I don't know how many people are familiar, I do the Atheist Debates Patreon project, which I post my debates, reviews of my debates. I talk about the arguments for the existence of God. Thanks. And I try to go into things in pretty good detail. So it's not just, here's the teleological arguments in short form. For example, the video on Pascal's wager is like 35 minutes long, and I go into great detail to talk about what Pascal actually said and how modern theists and Christians get it wrong. And one of the most recent videos that I posted in the last week, I think, is called The Beautiful and Ugly Truth, in quotes, about logical syllogisms. Because we get so focused on this idea of truth, which within philosophy there's disagreement about whether we have access to truth at all, when really, if you have a syllogism that's constructed in such a way that it's valid, we know that true premises lead to a true conclusion. But the truth is irrelevant in argumentation. If you are convinced that the premises are true and you reject the conclusion, you are by definition irrational, even if they weren't true, because you're now in conflict with yourself and you're in conflict with reason. Trying to establish a reasonable worldview is in part about internal consistency, so your worldview doesn't fall apart. But the goal, which is why it ended up on a t-shirt, I want to believe as many true things and as few false things as possible, is for my internal model of the world to match the external model as best it can. And I think science is the only way of knowing that you have that model. And philosophy is the background tools that allows us to make use of science and reason about it such that we can confirm the reliability of what we're finding from science.
Yeah, I mean, it's one way. I think that's, but I mean, and then, you know, scientists are doing philosophy, which I keep getting reminded about. It's fine. But that's what scientists are doing. They're confirming the reliability. They're using the tools of philosophy, if you wish, as practicing scientists, because they're continuing to do that. And the point is, which I wrote about in one of my books, but it's that there is no such thing as scientific truth.
Right.
Science is an approximation of reality, and it's always an approximation, and it describes all scientific theories, even quantum electrodynamics, that greatest theory we have, only works over a certain region. And so we have to realize that whenever we're saying things, we don't capture the whole truth, and that's fine. And what we progress is a little bit at a time. And as Feynman said, you know, maybe the universe is like an onion. You know, you peel back. There might never be a theory of everything. In fact, I'm quite skeptical of that. That's okay, because we'll learn a little bit more tomorrow than we did today, and be a little less falsehood on your T-shirt and a little more things that are not false, which is what really science can tell. Not that it's true, but just that it's not false. And I wanted, when you were talking, I wanted to comment about one thing, because I really like the three ways of sort of discussing that you described. And what I want to relate to people who may not know this is they were epitomized by one of my favorite people who's passed away, Christopher Hitchens, who was a friend of mine. And yeah, he's a great loss for humanity. But what people don't realize, because Christopher seemed like a bulldog on stage, was that, and he was, is that he was one of the most tolerant people of listening to others in life that I know. I mean, he would regularly have dinner parties with people that I would have a hard time being in the same room with. I mean, you know, Scalia was a regular guest of Christopher's at his house, and can you imagine? Could you have in any way? But he would love to. He loved to be able to not have an echo chamber, be able to talk to people about things and he and I had many debates about Iraq, for example, where we disagreed.
It's one of the few things that I disagree with him about. That and the wisdom of drinking scotch while debating, but he was far better at it than I was.
I want to tell you, can I say this? Yeah, I can, I guess. I was fortunate enough to give when in his memorial service, his wife asked me to give the speech, and then there was a lot of other minor figures like Salman Rushdie and Tom Stoppard and Sean Penn. And
I'm going to talk about you like this in the future.
No. Anyway, so I turned to Salman Rushdie, who stood next to me, and I said, people are going to listen to this program and say, who the hell is Lawrence Krauss? But anyway, but what's interesting is that my favorite speech was by another friend of mine who I just was with in England, Stephen Fry, who's wonderful. Do you know Stephen Fry? And yeah, he's great. But Stephen said when he disagreed with Christopher about, he said, Christopher once wrote that they're the four most overrated things in the world, and I think I have them right, were picnics, champagne, strawberries, and anal sex. Okay? And what Stephen said is I agree with him about 3 of those. Anyway, I just thought I'd say that.
So we want to make sure we get to your questions, which is always the thing that's most interesting for you, usually. Always usually?
Always usually.
I need to stop hedging
Is
my
that
bets.
a philosophical
If you've got questions, walk your ass up to the microphone.
Is there microphones? Yeah.
There's a microphone at the end of each aisle. If we can have the house lights up a little so we can see people's faces. Well, I'm not even going to add anything. I don't want to take any time out of your questions. We'll sum up at the end, I guess.
Yeah, sure.
Yes,
Or
sir.
not.
Oh, you need to actually get right up next to the mic, I think.
If it's on.
Thank you.
Oh, I hear it.
Working?
I hear it here anyway.
Okay.
Waves. So we can see waves at different scales: sound waves, water waves, electromagnetic waves, gravitational waves. To what extent is that just a superficial? Are they superficially analogous, or is there some?
Is this a question for me?
No, it's a really good question. Waves are natural because in physics, because really what I said about copying really works. The great thing about physics is very few ideas are needed to describe many different things. And basically, every time you have what's called a restoring force, so things are in equilibrium, and like that, happily that was restored, but every time you have a restoring force, so the situation is such that when you depart from it, there's something that wants to bring it back, you produce oscillations. And those so the same equation, which is called the wave equation, works ubiquitously throughout the universe for many different phenomena. You pluck space a little bit in general relativity, which means I wave my hands, because my hands bend space. So when I move them around, I'm bending space in a disturbing way. It creates a ripple that is like a pond, like a ripple on a pond. And similarly, I shake an electric charge, and that changing magnetic field creates a disturbance that ripples out. And it's the same. The wave equation is ubiquitous simply because in nature there's a restoring force, basically. So that's why it applies over so many different neat ranges of human activity. Good. That was a good question.
Sure.
Yep.
I have a question about ethics in science. Lawrence, you talked about how the scientific method mitigates against scientists' own prejudices and biases.
Yeah.
But how does it work with, guys who loved the physics so much that they created the atom bomb? How does science sort itself out when it comes to, just because we can do something, should we? And how does the scientific method deal with, unethical science things like animals, or like treatment of animals, or creation of terrible things?
I'll start, and you probably have some comments as well from maybe a slightly different perspective. But the science, what determines what should be done in some sense. Scientists will pursue interesting questions, but everything we do as humans can have good and bad consequences. Steve Pinker, another friend of mine, said very beautifully, I think, You know, people always say, oh yeah, scientists invented the atom bomb. But of course, atomic energy is incredibly also useful. And we can have nuclear reactors which don't produce carbon in the atmosphere if they're designed correctly and don't do bad things, which they can be. But they don't point out that that's true about everything. Architects can create beautiful buildings, but they can design gas chambers. And so what we need to do is realize that those are societal questions that society has to decide at some level, but only an informed society, only people who are informed of the issues and the perspective of science can then make a judgment. But scientists should not be ultimately making the decisions about how society uses the products of science. In a democracy, that should be people and our elected representatives, but those people and elected representatives need to have some scientific literacy at some level to make sensible decisions. But I don't think, but the scientists are going to discover principles that can produce wonderful things and awful things. And it's just the way it is, and it's the way it's always going to be. And to put your head in the sand and not think in advance about the awful possible things that can happen. Take CRISPR technology, which is an amazing technology that's used now to manipulate DNA in a way that would have been impossible 10 years ago, which could do wonderful things for curing diseases. But it also makes hacking incredibly easy. And it makes the possibility of creating smallpox viruses, for example, in simple laboratories, possible. And so we need to recognize we need to, as Louis Pasteur said, fortune favors the prepared mind. So I think scientists owe it to the public to explain what's happening and the possible implications of what might happen. And it's up to, in my opinion, the public to decide then how to create institutions and encourage the scientists to create institutions that help ensure that the products that come out of science have the best possible effect for humanity. But to pretend that these things aren't going to happen just because we don't like them, or pretend that they don't exist because we don't like them. As the Catholic Church, to bring it back to that, in vitro fertilization, which was condemned because the babies that would come out wouldn't have a soul, right? Until they came out and they were the same as everyone else, and then that stopped. But all those things are going to happen. Cloning people is going to happen, in my opinion, at some point. These things are going to happen because they're possible. But it's the scientific community, where scientific ethics comes in, is honesty and full disclosure, transparency, non-authoritarianism. Those are the ethics of science. That's what makes good science. And when scientists are unethical, it's for violating one of those things. But if they're honestly doing work, they're disclosing it, they're communicating with others, and they're willing to not censor information, then at some level, that's healthy science, and ultimately it's society that's got to decide which areas of science to fund and not. I don't know if you want to add to that.
I'm largely in agreement. This may be a slightly different way of phrasing the same thing, because I don't put the foundations of morality on societal opinions. But I do think that we evaluate the consequences of our actions, and you're not even the person who asked yet. I'm going to look at you.
I know. Yeah.
We evaluate the consequences of our actions with respect to some goal. You can't know what the consequences of some scientific discoveries are going to be. And so when you talk about ethics in science and scientific investigation, and there are two things to consider. Is the process demonstrably immoral? Are we chopping up people left and right in order to understand something better? We already know that that's wrong. So if there's no demonstration that the fundamentals of the process are immoral, we won't, then the next thing is to evaluate the consequences of what we discover. And you can't really know what the consequences are until you actually discover it. We could clone a person tomorrow, and we could find out that this is a really big deal, and we develop a better understanding of what is or isn't immoral about it, and then stop it. Or we could clone somebody tomorrow and find out that the things that we were afraid of aren't real. I don't know that as long as the process isn't immoral, I don't know that you could possibly say that any sort of discovery of a truth about the universe is itself immoral or so dangerous. You have to be able to find that discovery to know what the danger is going to be.
Yeah, I think, and that's why, that's why one of the reasons I'm happy I'm a physicist, and my lovely mother who's in the audience wanted me to be a doctor. and she got over it eventually, but it took a long time. But happily, there are, and when it comes to biology, there are many more immediate, more sort of ethical or moral questions. And the obvious ones, experimentation on human patients is universally agreed to be, immoral, but the good deal about, that's why I love what I do as a scientist, because what I do has no practical significance whatsoever.
Yes.
Yeah.
Okay, this won't be nearly as deep. This is going back to high school physics.
Good, it
I
was
need
getting
an
a little
answer.
deep.
It's bugged me for 30 years now. Why is the universe right-handed? With torque?
It's actually left-handed.
Is it left-handed? Why is the universe left-handed? When you apply torque in an XY plane, there's a force in the Z direction.
Well, that's
when you apply a
that
magnetic
part.
field and an electric field, it goes. You're playing in one plane.
I see. Oh, okay. You're asking a different question. I thought you were asking. Oh, that's just semantics.
Frozen accident?
No. I mean, because we have what's called the left-handed rule, right-handed rule in electromagnetism. So magnetic field goes around here, and or the electron, the current goes like this, the magnetic field goes like that.
Right.
Why is it that way? That's just because we defined it to be that way. If we change the sign of the charge, it'll be that way. So it's just an arbitrary.
Why perpendicular at all? If it's X, Y, why isn't it in that plane?
Is it?
What just kicks it out the other?
That is just the way it works. I mean, no, that's seriously. That's surprising. That the fact that a magnetic field causes a force on a moving electron that's perpendicular to its motion is an amazing discovery.
Actually, I know the answer. It's because of the Higgs field, but we won't be able to know that and prove me right for another 30, 40, 50 years.
No, but I thought the question you're asking, which is even deeper. So that's just convention. If you were on Mars and you called the electron positive instead of negative, they'd be using the left-handed rule instead of the right-handed rule. So that's just convention of naming. There's nothing fundamental about it. It's just the way we define directions. It's just words. But more significant is the fact that there are particles in nature like the neutrino that spin, and we call them left-handed if they're moving and they're spinning that way, and we call them right-handed if they're moving and they're spinning that way. Well, it turns out in nature they're only left-handed neutrinos.
Yeah,
and
that's
the answer,
what I mean.
And you know the answer to that?
No.
Okay. And
That's what I'm asking. It's
I know.
always in that.
I want to know the answer to that because we share that, because no one knows. And that's the exciting thing. We don't have the slightest idea why neutrinos are only left-handed. We think we've got a lot of ideas of why, and it may be related to why the universe is made of matter, not antimatter.
That's okay.
But we don't know yet, and we're going to try and find out.
So it's bugged you for 30 years and nobody else knows either.
Yeah, that's right.
Yes, sir.
Yeah. You can go. Yeah.
Okay, yeah. Can you hear me? Yeah.
I can hear you.
Thank you so much for being here tonight. On behalf of everyone in this room.
Oh, thank you. It's a pleasure. Thank you.
I guess couched in my question is an assumption you know who I'm talking about. Bob Duco is a Christian apologist out of Detroit. He is like, sort of like, oh my gosh, I've sat down with the most brilliant people like Lawrence Krauss. Dr. Krauss, is that true? Number one. Number two, Matt, I know Aaron has had a discussion with that apologist. Would you do the same? So first question, have you, in fact, sat down with Bob Duco or
no, I generally
chatted
don't.
with him? He quotes all the time that he has chatted with you in the Brilliant Minds and all that kind of stuff.
Well, he's chatted with me, but he's never chatted with me directly, and he won't. Because and it'd be interesting because we have different views about that because, well, Matt fulfills an important role, but I have debated, as in fact in Toronto, I recently was snookered into a debate with an idiot from the Discovery Institute a year ago. But I generally don't do it because I don't. First of all, I find formal debates to be rhetorical devices, not devices for education. So generally, I don't like. I'll do dialogues, I'll do discussions, but most often there are people who want to appear on stage. It's the same reason I won't debate UFO apologists on stage because they want to be on stage. Because then it gives them validity. It makes it seem like I take them seriously, and more importantly, the audience assumes that two people are honest and they both sound reasonable, and therefore it's he said, she said, or whatever. And what it does is it gives the illusion of equality when it doesn't. That's why I won't ever debate evolution versus intelligent design, because it makes it sound like there's a debate to be had. There's no debate to be had. I mean, there's no debate to be had.
So I have no idea who you're talking about, because despite what people think, I don't follow every apologist on the planet.
He's not a presuppositional apologist like your best friend Ty.
Well, he's off to a good start. Not a really good start, but a better start than some people I've debated. We're not far apart in our view of debates, but we're a little bit.
Well, Aaron Ra was interviewed, and they had an hour conversation. I'm surprised maybe you should. It was very interesting.
I'll ask Aaron.
Yeah. I mean, it was.
On the debate thing, though, I'm largely happy to debate almost anybody. There are exceptions. There are people I've debated before who I won't debate again, mostly because some of them are terrible people, not because they're just terrible debaters. Yeah. Also, there are people who, I don't like the idea of tiers, but if you get somebody who doesn't know anything, now all of a sudden in a debate, I have to backpedal so that it looks like I'm not being a dick. And I don't view debates I understand why he would view debates as primarily rhetorical devices, and I've talked about debate as primarily theater. Yeah. Because it's not necessarily who has the best argument. It's about presentation. It's about making a connection. It's one of the reasons why, and I don't think I'm telling tales, and if I am, Richard will tell me, if you want to do a debate in a Baptist church, you don't want Richard Dawkins, you want me. Because I have credibility with those people that he doesn't. In the same way that if you were talking science, you don't want me, you want Lawrence or Richard. I'm trying to fundamentally change the way debates are done, and I'm having some success at it. Because people, thanks. He who shall not be named.
Yeah, that's the way it should be.
Is a skilled debater, probably one of the best debaters Christianity has. But he's formulaic, predictable, and he wants only PhDs to debate. Because, and I'm sorry to all those people who are credentialed, I'm not just picking on you because I'm not. You can be overly educated in something such you forget the basics. And so there's a strategy to the debate where you get up and you say, in order for my opponent to win, they must do this, this, and this. Yeah. It is the collegiate scored debating format, and I couldn't give a rat's ass about that format because I want to have the conversation. And if you get people to break out of that format, where you have dialogues, where you have discussions, where you have debates that instead of 10 minutes, 10 minutes, 10 minutes, 10 minutes that are like joint press conferences, instead you say, here's my position, now let's go at it.
That's in
cross-examination. Those are the debates that I want to have, because guess what? A lot of those guys who are debating are basically thinking from a script. And I get to push back on that script and expose, is Cy ten Bruggencate just parroting what Greg Bonson said? Does he actually understand it at all? So I get to ask the questions that confound them. You know, when I was on a radio station, Minneapolis, St. Paul, they invited me back because they wanted me to debate Ray Comfort.
My good friend, Ray.
I said yes.
Yeah, sure.
He's a nice guy.
He's a real nice guy.
I really like Ray.
Diluted, but really nice guy.
Las Vegas. I saw that. That was
well,
we all saw it.
It was Washington where I was with him most. Yeah, with Washington, D.C.
But he showed up and he wouldn't debate. And he basically just said, I'm not interested in demonstrating the existence of God. I'm just here because I love Matt and I don't want him to go to hell.
Yeah.
Now, one of my biggest pet peeves is when somebody wastes my time. I get to waste as much of my damn time as I want. Nobody else gets to waste any of it. And so people who knew this said, oh, did you feel like this was a complete waste of your time? No. Because I was on drive time Christian radio with Christian parents driving their little Christian kids around, and they heard an atheist give all the good reasons why they shouldn't be believing what they believe, and their representative said, oh, I don't want to defend God, I just don't want Matt to go to hell. That was definitely not a waste of my time. The radio station was completely irritated that Ray pulled this little bait and switch on debate. Now, I'll never debate him again because he doesn't want to debate. I don't know about that apologist, and that was way long answer.
But you know, I think it's also useful that there are lots of 1,000 different points of light.
Seriously?
Yeah, seriously. As
No, I was
George
saying
Bush
that to
said.
Travis.
Yeah, okay. Oh, was he saying that we're done?
We have time for one more question.
Okay,
is
well,
what we were
okay,
just
then I
told.
won't say what I was going to say. Is that all we have? Time for one more question?
Two more questions is what we have.
Okay, let's be quick.
And as a reminder, and I apologize because I didn't know
Why is that? Okay.
we were going to ramble.
Maybe the theater's only...
You're signing books afterwards, right?
Well, I'm not selling them, but I'm signing them.
Signing books. We'll be out there. We can visit, and I'll stand outside if you want.
And by the way, yeah, I should say that is until they kick us out of the theater, out of the front, if we don't answer your questions here, and when I'm signing, I'll answer. Well, I'll stay here till the last person has a question. And
Plus, we'll come back sometime.
But out front.
You want to come back sometime? We can come back sometime too.
Oh yeah.
I'm happy to do that. Go ahead.
As long as they don't have to pay again. Okay.
Can you hear me?
Yes.
All right. So my question's a little bit off of this topic, but it kind of relates to some of the videos that you have on YouTube, Matt. I saw one debate that you had about whether or not humans have souls or not, and I think that you very much won that debate. The only question that I kind of have regarding that would be about near-death experiences, in particular out-of-body experiences, where someone is supposed to be considered like flatlined, their brain dead. Their brain is not supposed to be working, yet they report being able to see things that happened around them, and even in other rooms they're able to report conversations and things like that.
Yep.
And researchers have been kind of trying to say that this demonstrates that a soul exists. I just
they're
kind
wrong.
of want to know.
They're wrong.
And I can explain why. I can explain why pretty quickly so we can get on to the next question. When is it that they report this experience? It's after they've been revived. Now, so you've got a brain that's trying to make sense of what happened when it was not functioning. And you're also adding emphasis to the idea that a malfunctioning brain is going to give you more accurate information than a functioning one. And when we put it to the test, for example, you could put a sheet of paper that you could only see from hovering way above the operating table, and they've done these tests. Nobody reports what's on the paper. It's the idea of a soul is the single most dead concept in all of theology. And I'll do a video in part that goes into this in more detail. But everything we know about what's attributed to the soul is an identifiable, malleable part of the brain. To the point where even split brain patients, V.S. Ramachandran, look him up, he does a great talk several years ago about a split brain patient where they severed the corpus callosum, and you end up with two distinct personalities that communicate independently. One of them's a theist, one of them's an atheist. Go figure that out, soul advocates.
Yeah, absolutely. And the physiology of seeing a tunnel lighting and all these things as your brain is shutting down, the idea that the field of vision gets narrower and narrower. Everything that's been discussed is just,
And meanwhile, the religious imagery
believe.
that they see tends to coincide with what their religion is.
Yeah.
And so if there's different religions seeing this, they can't all be correct. They can all be incorrect.
And Carl Sagan said this in a beautiful book, which is famous before he died, the candle, what was it? Science as a Candle in the Dark.
Candle in the Dark.
He said, it's interesting that people report now seeing angels. In the 16th century they saw fairies, and in the 15th century, and it's interesting that it's always a thing, or aliens. I mean, it's always a thing that you see on TV.
The view of aliens changed.
Yeah, because somehow when people see these things, they're exactly what that culture is defined to see, but it's never constant.
Hey,
anyway, we should go to the next.
Go back to the beginning of the century, and what people described as aliens is very different. And suddenly, around 2001, they all become to almond eyes, and the stories get more similar. And it tells us more about who we are and how we're influenced than it does about anything in some supernatural realm.
Yes, Feynman said it's more likely due to the known irrationality of humans than the unknown rationality of aliens.
And you get the last question.
Yeah, which has got to be a great question, right?
No pressure. You should remember, we talked briefly about interesting and uninteresting questions up here.
Okay. If it isn't, maybe we'll go to the
better.
Okay.
Okay, so Professor Krauss, sorry, Matt, I rarely have an astrophysicist at my disposal, and I can call you next Sunday if I have anything to ask you. There's something that I've always wondered about, and it has to do with the heat death of the universe. I kind of get it, but I'm totally not a scientist, so I really don't. Does matter ever stop existing because the stuff that makes it up loses its energy? Do electrons deorbit? Does everything fall apart till there's nothing? Because I read A Universe from Nothing, and I'm wondering if we'll ever get back to that, to where there's a new universe.
Well, no, I talk about that in that book, but
I must
let
have
me,
missed that
well,
part.
clearly not clearly enough, but
I apologize.
no, it's a subtle and difficult concept. But so the point is that as far as we know, electrons don't decay. Okay, protons we think may decay, although they'll decay in such a long time that you keep your diamonds, as I said. But it turns out that there is a process that takes matter that we think, it turns it into radiation, and it's black holes. And so eventually, it's quite likely that most of the matter in the universe will fall into black holes instead of galaxies. And what is really weird, for reasons that is really strange, is black holes radiate. Stephen Hawking, that's what made him famous. And I mean, theoretically they radiate. We don't know for sure because we've never seen one, okay? But when they do, whatever fell in, it becomes irrelevant. You know, 2 Volkswagens or 1 Cadillac, it doesn't matter. What comes out is exactly the same, and it's radiation. And so in that way, that sort of processes everything and turns it into radiation. And so the ultimate state of a universe in which all the matter is collapsed in black holes will ultimately be a universe of just pure radiation. But the really neat thing is that it doesn't have to always be that way. Because if the universe is eternal, since, as I demonstrated, nothing is unstable, and what I mean then is that nothing is unstable. If you wait long enough, you'll produce stuff again. And so in an eternal universe, you'll have quantum fluctuations that will eventually produce a lot of stuff again. And so, in that sense, everything that was there will have disappeared, but other stuff can reappear. And so, you know, if that makes you feel better, great.
I can sleep again tonight. Thank you.
Okay, good. Thank you.
Thank you.
We'll do it again.
Yeah, let's do it.